Yeah, thank you very much. Thank you so much for the chance to speak here. My name is Simon. I work with Jonas Latz and Aretha Teckentrup, and I will talk to you about rational approximation for deep Gaussian processes. So I'm a bit more on the application and methodology side of things. So we're not using Umbridge yet in our project, but once our application gets a bit bigger, that would be a good option. So just to give you a bit of an overview of what I'll be talking about. First, I'll talk about my application that I have, as well as Gaussian process regression. Then we'll see why that might not be such an adequate tool for what we are doing. And which is why then I'll introduce deep Gaussian processes. And as a technicality that we have to deal with in our Gaussian process representation, I'll talk about rational approximation in order to give you a bit of a numerical insight into the tools that we use. So to jump straight in, what we aim at doing is we aim to solve an inverse problem. So I assume you're probably all quite familiar with this. The main points here are just that we have a linear map that transforms our quantity u here that we would like to know. And we unfortunately can only observe it through this linear map. And our observations are then also polluted by normally distributed noise denoted by eta here. And the application we're going for is, in this case, computed tomography. So assume you have some density, so in our case 2D, that we wish to know about. And unfortunately, we can't look into the patient. So what one would do in practice is one would take radon transform observations, or one would scan using X-rays, and that can then mathematically be represented as a radon transform. And that gives you observations, so which are shown on the right. So what you end up with is this sinogram here. And what you then would actually like to do is you would like to inverse this process. You would like to, from the data that you have, you would like to get back to your unknown, well, I should not use the term density in a probabilistic context too much, but say your unknown function u in this case. And the way that you usually do this is by Bayesian inversion. So what you do is you use Bayes' formula, you then make use of the prior distribution as well as the likelihood, which comes from the noise that you added or is determined by that noise term and its distribution. And together they give you a sense of what the posterior distribution of your unknown quantity then looks like. So your posterior distribution being the distribution of your unknown quantity u, given the knowledge of your data that you have. And quite often this is intractable, so you have to use MCMC in order to sample from this posterior. And the focus of this talk will be the prior distribution that we choose for our unknown quantity u. So as our application was spatial, one very common prior distribution to use in that setting is the so-called Gaussian process. You can think of Gaussian processes as being simply random functions, or in a vague hand-wavy way, as an infinite dimensional normal distribution with a mean that is usually chosen as a zero function and some covariance operator that gives you some structure of your random functions. I'm not going to spend too much time on this in order to speed things up, because what we'll be looking at is a very specific class of Gaussian processes. So what we'll actually be using as a representation of our random functions is the following. So the class of Gaussian processes we're looking at is Matern type Gaussian processes. And these have been shown to be the solutions to a stochastic PDE. And we use this PDE to represent our Gaussian processes. So how does this work? In our PDE, we have this differential operator raised to some power, some fractional power. And this multiplied by our Gaussian process or random field gives us a right-hand side term, which is scaled white noise. So in order to obtain a sample from your Gaussian process, you could then make use of this stochastic PDE by drawing a sample of your white noise, solving this PDE, and then what this gives you is a sample of your random function u in this case. And the properties of your resulting Gaussian process are determined by the parameters that we use in this representation. So I have highlighted these two parameters that I'm using, where alpha can be seen as a bit of a regularity parameter, and kappa, then once alpha is set, determines the length scale or correlation length of your Gaussian process. So to illustrate that, on the left, I'm fixing our value of kappa, and I'm just changing the regularity parameter. So for regularity parameter of 1, we have very non-smooth, in fact, non-differentiable samples. For alpha equal to 2, they become once differentiable. Alpha equal to 4, they become much more smoother. So that's kind of the action of our regularity parameter. And when we fix our regularity parameter, and instead we let the kappa vary, so our length scale parameter, we can then observe that for very small length scale parameters, our actual correlation length will be very large. So function values of our sampled function values of our random function on the right-hand side will be very close to what we have on the left-hand side. Whereas when we choose a very large length scale parameter kappa here, then the correlation length will actually be very small. So function values on the one hand side are very much decorrelated from function values on the other side. So this is the way we represent our random functions or Gaussian processes in this case. And these were just 1D examples, but of course the whole thing also exists in 2D. So going back to our original inverse problems, we now want to see what happens when we use a Gaussian process, or the Gaussian process I was showing you as a prior for this problem. And in order to then get a solution, we just take the mean of the resulting posterior distribution. And since we're doing standard Gaussian process regression, there exists an analytical formula for that. So the result of that is given on the right here. And as you can see, it's quite a good reconstruction because we've given it tons of data and the noise level wasn't too bad. But if we look at the error a bit more in detail, we can see that not only our image has been reconstructed, but also the entire noise is still there practically. So we have noise all over the image, especially in the corners here. And the reason for that is that for this reconstruction, I have chosen a rather large value of kappa. So a large value of kappa means a small correlation length, which means that not only do the small scale features of the image get reconstructed, but also the noise. So we do not want that, obviously. So what you could do instead is choose a smaller kappa. So this then just gives you this result. And once again, checking the noise, we can see that now what this effectively does is that it does reduce the noise, especially in the corners and around the edges, quite nicely. But unfortunately, we now fail to recover the small scale features of the image. Most notably, we make a big error around this edge here. So the edges and contours of the image have been smoothed over. So this basically goes to show that using only a single length scale does not work when we want to reconstruct images. So when we want to reconstruct images, we want to be able to both reconstruct areas that are rather flat as well as areas that change a lot, such as edges or contours. And at the same time, we'd like to smooth out the noise as well. So standard Gaussian processes do not seem to work. So that is why we go into deep Gaussian processes. So deep Gaussian processes are basically called deep because they build a hierarchy of Gaussian processes. So the way we construct them is we start with one Gaussian process, in this case U0, and then we define the next Gaussian process U1 that depends on our original Gaussian process through this relation that the covariance structure now depends on the values of the lower Gaussian process. And this is going to be the key to including multiple length scales in our model, basically. It might also be important to note that this deep Gaussian process construction is not unique in the sense that people use the term for many different things. So yeah, there's an overview in this paper by Dunlop et al. But we just use this very specific construction. And even more specifically, the way we implement it is that we change this covariance structure here, depending by making use of the length scale parameter kappa. So we now choose kappa to be a non-stationary function, and specifically we choose it in such a way that it depends on the values on the lower layer. So now our upper layer U1 can represent length scales that are given by this non-stationary kappa of x, which depends on our bottom layer. And then, yeah, the exact expression for layer transformation, that is just the way that we've chosen it because it works well, but importantly, you have to be bounded from below and from above to be able to make sense of this in your SPD context. That is the main key takeaway message here. And technically, you could add more layers. So you could add U2 that depends on U1 and then U3 that depends on U2. But for this case, we just stick with 2 layers. So just to illustrate that a bit more, what the deep Gaussian process that we are looking at looks like. So this is just one sample of our deep Gaussian process. On the bottom layer, it is simply a standard normal vanilla Gaussian process. So there's nothing interesting happening here, so to speak. But if we look at our U1, we can now see that the correlation length structure or the covariance structure of this sample is very much influenced by our bottom layer. So in areas of large values here, we have very fine grid, small detailed structures around here. And in areas of small values, we are very smoothed out because of the transformation we have in between our layers. So what happens when we use this Gaussian process as a prior distribution for our unknown quantity is the following. The first thing that happens is that we cannot make use of the formula for Gaussian process regression anymore. So now we actually have to use an MCMC scheme in order to get samples, and then from those samples we can then compute mean values as well as doing other uncertainty quantification. And if we then look at the mean of our top layer, we see that it recaptures or reconstructs the image quite nicely. And we also get a bit more, so we now also get a bottom layer, which in this case I've already transformed to give an indication of the kappa value that is equivalent to. And in this bottom layer, we can see that we have actually managed to find the edges of the image quite nicely. So we can see the contour here. We are starting to see some details on the inside emerging as well. And if we then look at the errors that we make, we can see that we have kind of achieved what we were looking for to some extent. So the error around the corners is quite smoothed over quite nicely, but we still managed to recover and reconstruct the contours reasonably well. So just to show that this is actually true, here's the error plots of all three results next to each other. And on the right-hand side, we kind of combine features of the two earlier cases. So we combine the reconstruction of the inner bit that we're actually more or less interested in, but we also combine the smoothing over of the error. And in the middle, unfortunately, what you can see is that we also smooth over the contours in the middle, which in this case can't be helped. So yeah, so that's been a very quick introduction to our application and what we are actually doing. Anne, do I still have time, or should I wrap up?
You can continue. You have about 5 more minutes or so.
Okay, great. Thank you. So as a technicality, as I was mentioning, in the end, the way that we represent our Gaussian processes is via this stochastic PDE. And there's a few things why this is a bit not as straightforward as it may look or may seem. And a lot of these have been dealt with quite well in literature already. So just to give you a quick overview of that, we usually have to introduce boundary conditions because we can't solve our PDE on the entire space of RD. And by introducing these boundary conditions that we then have to guess, we forcibly introduce an error. Also, the white noise does not take values in functions, in function space, but only in distribution spaces. So that is something one has to be quite careful about. But luckily, this makes it well suited for use in finite element method schemes. And finally, we're coming to this fractional operator here. So this fractional operator, whenever a over alpha equal 2 is a natural number, then obviously we'd be fine, but we don't want to restrict ourselves to such cases. So the big question is, what do you do if you actually have a fractional operator here? And in order to deal with that, let me just briefly introduce a discretized version of this inner operator here, and then the brute force method to still make sense of that fractional operator would then to just take the matrix power of this discretized operator. But in practice, this is going to be way too expensive, so we cannot really do that. But which is why we are looking for a different approach. So in our case, that is rational approximation. So in rational approximation, you approximate the function that you're actually looking for, in this case, in a scalar sense. So z to the minus alpha over 2 by using a rational function. And yeah, the hope is then that if you then plug your discrete operator into that rational function, you kind of recover the behavior of the exact matrix power. And in practice, this ends up working quite well, or in our case, it does. So yeah, I'll go over this a bit more quickly. But yeah, this is basically the gist of what we're doing. So there is a very nice algorithm, luckily online, that we can use to compute this rational function. It can also be shown that most methods for solving fractional PDEs are in fact rational approximations, so there's not too much worry that one misses out by not keeping track of the whole literature of the field. And also we can show that the error when the discretization becomes smaller, that the error also will become smaller if we choose the rational approximation as well as our finite element method correctly. So that is not entirely trivial because of the presence of the white noise on the right-hand side. I think I'll just skip over that as well. And then, yeah, hopefully in this talk I've been able to show you that deep Gaussian processes can model, well, non-stationary data, such as images, quite intuitively, as well as being a reasonably fast tool. So we use this stochastic PDE especially to avoid the common bottlenecks of Gaussian processes by making use of existing PDE solvers. And then finally, using the stochastic PDE does not necessarily mean that you have to restrict yourself in terms of the regularity parameter too much. But using rational approximation, we can overcome those problems as well, basically. Yeah, that is it for me. Thank you very much. And I'm happy to take questions.